Hi everyone, in this short video I'm going to talk about the normal distribution. I will show you how to compute probabilities for certain given z-score using statcrunch and table, and also briefly talked about the empirical rule. The normal distribution, originally called the Gaussian distribution, it was named after Carl Gauss, who published a work in 1833 describing the mathematical definition of a distribution. This is also known as Gaussian distribution. Normal distributions are bell-shaped, but the bells come in various shapes and sizes. And note that mean, mode, and median are equal in normal distribution because they are symmetric. Just to show you the probability density function of the normal distribution is given by this expression, where this little x is the observation, mu is the expected value or mean of the normal random variable, and sigma is the standard deviation, and this pi is constant. If a continuous random variable x follows a normal distribution with mean mu and standard deviation sigma, the notation we write is x follows normal distribution with mean mu and variance sigma squared. This is how we write. What I'm saying is, if you give me mean mu equals to 10 and sigma equals to 5, we write normal with mean 10 and variance 25, 5 squared 25. That's how we write. Or you can just say n 10 comma 5 squared. This is what I'm saying. That is just a notation you may see in your textbook. Let's talk about a couple of properties of the normal distribution. First, the total area under any normal curve, bell-shaped curve, equals 1. A normal distribution is the proper term for a probability bell curve. And like I said earlier, normal distributions are symmetrical, but not all symmetrical distributions are normal. Just to clarify, before I clarify the empirical rule, within a fixed number of standard deviations from the mean, all normal distributions contain the same fraction of their probability. So what I'm saying here is that suppose this is mean, mean is, the notation is mu, and standard deviation is sigma, then in any normal distribution, about 68% of the observations fall within one standard deviation of the mean. What I'm saying is, this is this guy 68.27, so about 68% of the observations lies here. And similarly, this is mu plus 2 times sigma, meaning mean plus 2 times standard deviation, and on the left side, mean minus 2 times standard deviation. About 95% of the observations fall within 2 standard deviations of the mean. All right? And similarly, about 99% of the observations fall within 3 standard deviations of the mean. So this is what we are saying. Just to clarify here, suppose mean mu equals to 50 and standard deviation is 10. So this is 50. Now 50 minus 10, that is 40, and 50 plus 10, that is 60. So about 68% of the observations lies in this interval. Similarly, you subtract 2 times 10, you go 2 standard deviation away, so that would be 30, and on the right I have 70. So 95% of the observations lie in this interval, 30 and 70. And similarly, the 3 standard deviations, about 99.7, that means 30 minus 10, 70 plus 10, 80. So that means 99.7%, about 99% of the observations lie in this interval. So this is known as empirical rule. All right, so just to continue here, if the mean mu equals to 0 and standard deviation is 1, this is known as normal random variable, and it's denoted by z, and we write normally distributed with mean 0 and variance 1 here. If you have this situation, x is normally distributed with mean mu and this variance sigma square here, then the random variable technically is similar to the standard score that you have. That's how we calculate. X minus mu divided by sigma is the standard normal random variable with mean 0 and standard deviation 1. So that means in this case, this mean would be 0, and you are talking about 1 standard deviation, 2 standard deviation, and 3 standard deviation, and this is what we are talking here. All right. Now, G transformation. The G score represents the number of standard deviations from the mean. All we do is the given observation minus mean divided by standard deviation. This is how you do, and you may see this notation. And let me talk about how you compute and how you compare test scores that use different scales. So meaning G scores can be used to compare observations from different normal distributions. For example, there are 2 situations here. First, you scored 650 on an SAT exam which had mean 500 and standard deviation 100. So we are talking about the G score for SAT exam would be the observation, technically x minus mu divided by sigma. That gives me the G score of 1.5. For ACT that your friend took, scoring 30, that is the observation, minus mean divided by standard deviation. So that gives me the Z score for ACT. So this is higher than this. That means ACT score is better, even though its numerical value is smaller. Right here I have 30 and 21, and you are talking about 650 and the mean 500. But looking at these standard score, we are able to compare. So that means the ACT score is better in this case. Next, we talk about finding probabilities using the standard normal table. There are various types of tables. So this one is talking about the area, less than this G score here. So these tables gives me the cumulative score that is less than this G. So technically, if you want to find the area this side, all you do is 1 minus this area. Let's look at an example here. For example, you want to find a probability of a certain Z score less than or equal to 0.40. So in that case, when you go to when you look at on the left, that is, you look at 0.4 right there, and you look at 0. So 0.40. So that gives me 0.6554. So what I'm saying here is this is A, this is B, and this is C, the way they are explaining here. The crosshairs created when we look right of A and down from B gives us the less than probability for that G score. Now you can do this easily in StatCrunch. That you just log into the statistical software that we use in this course and go to Stat Calculators, and you go to Normal. Now you have this situation. This is saying standard normal distribution with mean 0 and standard deviation 1. Now we are talking about the Z score that would be less than or equal to 0.40. And when I compute, I get 0.6554. So you can see that the area less than this. And by the way, just to let you know, if you want to find area greater than this, then you can subtract this from 1, or you can use this notation and compute. All right. And 0.6554 you can see here, right here. Just to continue, similarly for 0.25, I'm looking at 0.2 and 5, 5987, 0.25, 5987, which is right there, 5987. One more example here, which is very important, and you will have these tables while taking the quiz or exam or working on the homework. Let me show you these two situations here. The first one is talking about a mu plus Z sigma, and remember here Z is 1.12, and this is talking about greater than. So basically this one is saying probability of Z greater than or equal to 1.12. This is what we are talking about here. So in that case, I need to just switch this sign, greater than or equal to, and then you look at you enter the 1.12. So that means 1.12. Compute, I'm getting 0.1314 in 4 decimal places. 1314 in 4 decimal places. Similarly, for this case, it's a little bit different, but which is pretty interesting here, because think about this is 0. Now I'm talking about negative 0.91 and positive 0.91. So you want to find this. That means you can, there are several ways. So you can go here and you have here between. Previously I used standard, now you go to between. Now I'm going to plug in negative 0.91, that is my negative z, and then positive 0.91. That should give me negative 0.91 and positive 0.91. So that should give me 0.6372 in 4 decimal places. 0.6372. That's how you compute the probabilities of standard normal distributions for given z-score. All right. Reach out to me if you have any questions on any particular problem. I will be glad to help you.